Graphene oxide is extremely versatile, with potential applications in many engineering fields. But for its effective use, control of its structure is essential. For instance, thin films and membranes require highly ordered nanoparticle arrangements, composites require dispersed nanoparticles, and hydrogels require 3D porous arrangements. However, the structure of graphene oxide can vary significantly depending on its fabrication process and the amount of oxygen it contains. This makes its characterization difficult, which in turn makes it challenging to understand the link between the structure of a graphene oxide flake and their final morphology in composites. In a recent study conducted at University College London, scientists used a technique called multiscale modeling to gain insights into the driving forces behind the formation of different graphene morphologies. Using two polymers, polyethylene glycol and polyvinyl alcohol, they conducted bottom-up simulations in which they observed how changes in the chemistry at the atomistic scale propagate up and ultimately shape the properties of graphene flakes and graphene oxide composites at much larger scales. For each polymer, they studied the thermodynamically stable microstructure, morphologies, and dispersion mechanisms for various oxidation levels. Because stable dispersions are important in many commercial applications, one relevant finding is that the flakes never disperse in polyvinyl alcohol and only disperse in polyethylene glycol when highly oxidized. The scientists were able to validate their modeling results against the extensive literature on graphene oxide systems in organic solvents, past X-ray diffraction measurements of the interlayer spacing, and transmission electron microscopy images of aggregates. Overall, this study explains the sometimes unpredictable morphologies of graphene oxide and provides tools and rules to design new synthesis routes for desired graphene structures for various applications.